for in a lot of different transformations. But uh, one of the things to point out about the reaction is that it involves the loss of water, right? And you have to do it with a primary amine. Right? You have to do it with a primary amine. So a primary amine reacting with an aldehyde or a ketone is going to give you an imine. So let's talk about how that happens, the mechanism for that, and then we'll talk about the Gabriel synthesis, and then we're going to go back to that handout that we were doing. Am I on a page break? Yep. Oh, I hate when that happens. All right, so let's take the zoom in. We're gonna do it on an aldehyde. So I'm gonna take just a plain simple aldehyde. Yes. Okay. All right, so I have my primary amine and my aldehyde, and when I react them together, what do you think the first thing is that happens? All these carbonyl reactions kind of follow a similar pathway. So what do you think happens first?
Protonation.
Protonation? Not in this case. In this case, it's going to be attack of your amine on your carbonyl. That's normally, unless you have a proton source present, normally the first step is going to be nucleophilic attack of your amine on your carbonyl, right? And then you're going to get the tetrahedral intermediate that's common to all these reactions. I'm gonna put the amine up top so you can see, or that'll help you figure out what the next step is.
Is that an N?
Say again?
The amine is an N?
Yeah, it's a nitrogen. All right. So once that attacks, this is positive, by the way, right? And then oxygen has 3 lone pairs and is negative. So once that attacks, you go through a series of proton transfers, right? You do one here. Right, so you do a proton transfer there. That's going to give you right this amino alcohol, and then we want to get rid of water. So what can we do to lose water, or make water first before we lose it? What can we do?
Another proton.
Take another proton. Right, just like that. Why is Dr. Brumfield calling me? Let me answer this. I'm sorry. Hey, Dr. Brumfield.
Hey, Dr. Russell, did you see my email?
I did not. I mean, I was in class.
Oh, I sent it last night.
I didn't.
need the time and efforts. Check.
Okay, I got you. I'll send it today. I promise.
Yeah,
As soon as I'm done with class, I'll send it to you.
yeah. Look through them and just fill them out and send them for me.
Okay, no problem.
All right, thanks a lot, dear.
Thank you.
Bye bye.
Sorry. So now you have this hydronium ion, right? Now, how would you get rid of water here? What would you do?
Break that bond.
So you want to break the carbon-oxygen bond. I agree with that. But you can also do this, right? And that nitrogen actually forces water out. So that's how you end up with
Dr. Russell, it's kind of breaking up for us.
going on.
The connection. I'm going to leave and come back. Let's see.
Yeah, I'm gonna have to. Just give me 1 second.
It's
Can y'all
cool
still hear
now.
me?
Yeah.
I don't know what happened. This computer is sucky. That's all I'll say. Let me try to share my screen again so we can finish that mechanism. What's going on? All right. So the amine, again, you make that by using a primary amine, which we have right here, and an aldehyde or ketone. All right, and when you react those two together, it's just a nucleophilic attack followed by 2 proton transfers, right? And then elimination to give you to lose water and give you the amine. All right, so this is my elimination step right here. And then these are my proton transfer steps. So you got 2 protons. You have a nucleophilic attack step. Followed, and the last step is an elimination. All right. Any questions about that? About the amine formation? So again, the amine is it's a very important functional group. It's common to a lot of different molecules like natural products and things like that have biological activity. So yeah, so that's that. And then the last reaction that we're going to talk about with amines is how to make them from alkyl halides. So that's what this reaction is right here. This Gabriel synthesis. I just want to put it on a separate page so I don't have to worry about. Right, so for Gabriel synthesis, this is a way to synthesize amines. And you synthesize them from alkyl halides. Right, so you got the reagents that are shown. Right, phthalate, which is the source of your nitrogen. Right, so that's your nitrogen source. And then the alkyl halide, right? And then a base, right? So you need a strong base. And we're going to talk about what the purpose of that is. Right, so you need a base, you need phthalate, and you need an alkyl halide. So those, when you see phthalate, then you know that you're doing a Gabriel synthesis. If it's phthalate plus an alkyl halide. One of the things that you shouldn't get caught up on is this diacid. That's the side product. That's not the major product. Gabriel synthesis is a way to make amines from alkyl halides. Right, the diacid is a side product that we don't care about. All right, so let's look at the let's look at how this works. All right, the first step is deprotonation of the phthalate. All right, that's why you need the KOH. So I'm gonna draw that out. All right, so the KOH, obviously the base part of that is the hydroxide. So I'm here and pull that proton off. Oh man. All right. Let me know if it starts breaking up again too. All right, so you end up with this. All right, so you end up with this anion plus water. And then that anion is now that's gonna be your nucleophile that reacts with your alkyl halide. So whatever the alkyl halide is, it doesn't matter. And you can make primary or secondary amines using this method, right? But we're gonna just use a primary alkyl halide, something like this. So at this point, it's just a substitution, right? An SN2 substitution on the alkyl halide, right? So you end up with I'm gonna cheat just a tad. You end up with that as the product. And then in the final step, what you do is flood this, like, so when you see the water up top, right here, right, you just add water and that pops the ring open here. So water will add here, basically in a hydrolysis. All right. And so let me just show you what you get from that first step, and then we can explain the rest of it. All right. So after you add water once, right, that's going to attack that side, and you end up with this. Hold up. Let me fix that. Like that. Then you add the second water, and it attacks the other amide on this side. Right. And so now you get this diacid as one of your products. It's the side product though. And then the amine. Add a carbon. All right. So that's a primary amine because I started with a primary alkyl halide. All right. You want a secondary amine, then you start with a secondary alkyl halide. All right. Any questions about the Gabriel synthesis?
No.
All right. So let's go back. Let me put the dates on here too. So when I post it, what's today? The 2nd. That's so crazy. It's already November. All right. Let's go back to here. All right. So we have here, we did this reaction already. We were at this last reaction where we had this alcohol in the middle, first reacting with chromic acid to give the aldehyde, and then reacting with methylamine in the second step to give the amine. So now that should be a little bit, you should have a little more clarity as far as that reaction is concerned. All right, so let's go down to the next set of reactions. So we just predicting the product. So we have a carboxylic acid plus ethanol. What should we get from that? You got 4 choices. Let's start there, right? It's not going to be this.
The third one.
Is that right? All right.
The
What
third
happens?
one.
Go ahead.
I was saying the third choice.
It's an esterification. Is that right?
Mm-hmm.
Yeah. You have a carboxylic acid and you reacting it with an alcohol. That's how you make esters. All right. What about in the next example?
That first choice.
What's the reaction called? You're right. Thank you. You got two equivalents of alcohol and you have a ketone. So you're gonna get a, why wouldn't it be the second choice?
Where did the alcohol go?
Hmm?
Where did the second alcohol go?
You mean
That would be like the middle of the process, wouldn't it?
yeah, good. So the second choice would be the hemiacetal, but since you got two equivalents of alcohol, then you're gonna make the acetal. If it was just one equivalent of alcohol, then you would get the hemiacetal. Good. Well, all right, well, what about the third question?
The third choice?
Yeah. Why'd you sound skeptical about that? Right? You have phthalate, right? You got an alkyl halide, strong base, and then water, right? This is, again, anytime you see phthalate reacting with an alkyl halide, it's a Gabriel synthesis, right? You should have a flashcard for this. You should have a flashcard for acetal, hemiacetal. If you take the handout with all the reactions on it, that's your guide for making your flashcards. And what I've done in the process is also giving you the mechanisms for those reactions, right? And so this is a Gabriel synthesis. All right, I had another, shucks. Let me grab this other handout right quick. Any questions about that? I need to grab a handout from Blackboard. Give me 1 second. On that handout that we just finished, you can skip the aromatic part. You don't have to do that. Let's see which one this is. This is what I want right here. All right. Should have added to that. Yeah, good. All right. Let's do the reactions in this wheel. We're gonna work around it, and then we're gonna work through a bunch of other reactions down here. The only thing that I haven't talked about is right here, epoxide opening, but we'll get to it. All right. So let's go to the reaction wheel. Let's start working our way around that. All right. Where do you want to start? I guess that means you don't want to start. But we got to start. So we'll start at 6 o'clock. Right here. All right. What reaction is that? It's the alcohol is the functional group that's getting reacted on. What reaction is that? When you have a base plus an alkyl halide, and then you add a base plus an alcohol, and you add in the alkyl halide.
Is it the Williamson's?
Yes. Good.
The ether synthesis.
Mm-hmm. It's Williamson ether synthesis. So what does that do? I'm just going to abbreviate that. Right? It turns alcohols into ethers. Is that right?
Yeah.
So the CH3 from here, from the alkyl halide, that CH3 ends up, my pencil's too thick, sorry. That CH3 ends up replacing the proton on the alcohol. Right, so that CH3 ends up here, so you make an ether. I think, let me just say this too, and based on years of teaching this class, the biggest problem with this section is knowing your functional groups. So if you don't know your functional groups, you're gonna kind of stumble. My suggestion is to go back and look at your notes from part 1, or look at the chapter in the book. I think it's chapter 2 or 3. It might be chapter 3 in the new book, dealing with functional groups, because that's one of the biggest impediments to this section is not knowing those functional groups. All right, let's go to, I'm going by level of difficulty. Let's go to this next reaction right here. We got potassium permanganate, reacting that with an alcohol. What is it going to do to that primary alcohol?
Oxidize it.
Oxidize it. Good. To what oxidation state? Is it going to be the ketone or the aldehyde, or is it going to be the acid?
The acid.
Acid. Good. So we're going to take this. And that alcohol is now going to get converted into an acid. Sorry about that. I lost my other stylus, so I had to go old school and go back to the one with the little rubber tip. It's decent though. I actually like it better. It's just too short. All right. Now, what's the next step? If I got the acid and now I'm reacting it with a alcohol, what am I going to do there? We just did this reaction on the other worksheet. Am I right? Anytime you have a carboxylic acid and you react it with an alcohol, what do you get? Here's the easiest way to think about that.
Is it a carbonyl?
Say again.
A A carbonyl?
Yeah, well, the carbonyl that's a generic term, right? This is anything containing that can be considered a carbonyl, but the more specific carbonyl that you get is going to be the ester. Right? It's going to be a esterification. So the alkoxy part of the alcohol is going to swap out with the hydroxyl group of the acid, right? It's a condensation reaction. So I'm going to end up with this. Right, and then plus water.
That pH supposed to be a replacement of the ring?
Yeah, it's just a abbreviation for that benzene ring. Did we talk about that when we did aromatics? About how you can write the benzene ring as, if it's a substituent, you can write it. You call it a phenyl group. And so we just abbreviate it as pH. All right. So that's a oxidation followed by an esterification. Let's go to this side. We have chromic acid and a primary alcohol. What is that going to give me?
An aldehyde.
Good, good. It's going to oxidize that alcohol up to the aldehyde. That's exactly right. So I'm going to have this aldehyde. Right. And then
He scrolled back up. Wait, no. Okay.
Yeah, everything is acting stupid today. The tablet and the computer. All right. So that's an oxidation. Is that right? And then in the next step, what reaction is that?
The Witting reaction.
I heard somebody say it. Can you speak up some?
Is it Witting?
Yeah, it's a Wittig reaction. Good. Right. What does that do? What does the Wittig do?
It converts aldehydes or ketones to alkenes.
Yes. All right. And so without going through the mechanism, let me show you what we talked about before. Right. Do you see whether that the carbon right here is the carbon that contains the halogen? Right. And so in order to predict the product, because it's not asking you for the mechanism, if you subtract HBr from that, I know it's kind of a wonky way to do it, but just bear with me. So we have CH3, CH2, and I'm gonna draw that out because I want you to really see what I'm talking about here. Right. So that's my alkyl halide, and if I remove one H and one Br, what am I left with? This doesn't change. But what's left now on that carbon?
It's just the
One
hydrogen.
hydrogen.
Just a hydrogen. Perfect. That's the carbon right there is what's going to replace oxygen in that carbonyl, in that aldehyde. Right. So when I draw the product now, it just looks like this, right? Cheat again. So instead of that being oxygen, I'm just going to replace it with the carbon. C, H, and then I'm going to put the CH3 up here. So again, the way you predict a product, if you look at your alkyl halide, wherever that halogen is, whatever carbon that halogen is attached to, all you do is take off an H and take off the halogen, and what's left, that carbon is the carbon that replaces the carbonyl oxygen. So that carbon is going to replace this oxygen right here. So you're going to take off H and Br now from the same atom. You can't take the H from one place and the Br from another place. They both take them both off the same atom, and that carbon that's left, that's going to be what replaces your carbonyl. All right. Any questions about that? All right. Let's do the last reaction. This reaction is actually going to take place on the alkene. You got hydrogen peroxide, sodium hydroxide in the first step. Second step, sodium methoxide. Which is just really a good nucleophile. Hold up. If you got an A in part 1, you should be able to tell me what that first reaction is without hesitation. Or with a little hesitation. Or with some hesitation. All right. With a lot of hesitation. So hydrogen peroxide and sodium hydroxide, if you react the alkene with that, it's going to be, and that actually was in one of those the video I sent too. That's an epoxidation. All right. So the product from that reaction is an epoxide. Anybody remember that from part 1? Well, you could hear a rat pee on cotton. It's quiet. It got quiet for real. All right. So that's it. That's your epoxidation. There's another way to do it too. Anybody remember that way? Let's see if I can refresh your memory or jog your memory. Try to anyway. So epoxidation is when you take an alkene and some type of oxidant and convert it into an epoxide, which is a cyclic ether. All right. So you can do this two ways. You can use hydrogen peroxide and sodium hydroxide, and that'll give you an epoxide. Or you can use MCPBA. And that'll also give you an epoxide. The MCPBA is mostly for electron-rich alkenes. And then hydrogen peroxide is better suited for electron-poor alkenes. Right, but both methods work to give you epoxide. Let me just show you the first one. Right, so when you use that peroxide, first thing that happens is the peroxide gets deprotonated by sodium hydroxide. Like that. So now you got this peroxy anion plus water. And then it's this anion that's going to attack your alkene. Right? And it's that simple. So the alkene is here. So you've got this peroxy anion, and then in step 2 is going to be alkene attack. Right? So you have an alkene like this. The peroxy anion is here. That's negative. That attacks here. And then this attacks here. Right, so the oxygen attacks, and then the alkene attacks oxygen. And then you end up with the epoxide. right? So your epoxide that's another really common functional group. Pretty important functional group too. And you can actually open it up. Right. So let me give you one last example, then we're gonna stop. All right. So if you got an epoxide, right, you can open it with a good nucleophile. So if you have an epoxide, let's do this. So you got an epoxide like that. If you treat it under neutral conditions, it's going to open at the least substituted site. So it's going to open at the carbon that's highlighted in blue. So if I just treat it with sodium methoxide, and then later acid, because you're going to have to quench it. Right? I'm going to end up with this alcohol. Right? And you can see, again, the OCH3 attack that least substituted carbon. Right, it went right there, boom, and popped that ring open. All right, if I treat it with acid first, so if I first treat it with acid, and then treat it with sodium methoxide, right, that gives me a totally different product. This is going to open at the most substituted side. Right, so under neutral conditions, it opens at the least substituted side. Under acidic conditions, it opens at the most substituted side. Right, so instead of your alcohol being on the carbon that's highlighted in purple, it'll end up on the other side. So let me just draw that out real quick. So your alcohol will end up here, and then you have Well, now the OCH3 attacks here. And this is in the last video that I sent out. Right. So the opening of an epoxide is going to be dependent on the conditions. Again, neutral conditions is going to open at the least substituted side. Acidic conditions is going to open at the most substituted side. All right. Any questions about that? All right, we got to stop here. I'm going to upload the notes and I'll upload the video and all that good stuff in a second, if there are no questions. All right, so we're going to stop right there. We'll pick up on Wednesday, God willing.
Thank you, sir.
All right, y'all have a good day.
Thank you.
Have a good day.
Have a blessed day.
Okay.